and welcome to my video lecture. This video's topic concerns the role of memory storage in the LC3. Here, you can see the full data path of the LC3, including interrupts and exceptions, as well as input and output. To better understand the importance and role of different memory storage types in the LC3, I have broken the storage up into 6 distinct groups. Group 1, memory. Group 2, the register file. Group 3, registers used by LC3 programs. And, while covered outside of this video lecture, there is the control unit, interrupt memory, and input-output memory. From here on out, I will be using the simplified version of the LC3 data path to avoid the clutter from the component not discussed in this lecture. First, let's explore the role of the memory unit, which consists of the RAM, the memory address register, or MAR, and the memory data register, or MDR. The RAM is the main memory storage in the LC3. It is of the size 2 to the 16 by 16, or an equivalent storage capacity of 128 kilobytes. The MAR and MDR are the tools through which the LC3 not only obtains information from the memory, but also controls when and how this information is processed. This is a close-up look at the interaction between the RAM, the MAR, and the MDR. A 16-bit signal is passed from the bus to the MAR. If the load MAR signal in the control word is set to a 1, then this information overwrites the pre-existing data in the MAR and passes the signal to the address line of the RAM. If the value of the read-write signal is a 0 and the MIO enable signal is a 1, allowing use of the RAM, then the RAM chip will parse the data in the MAR as a memory address and will send out the data stored in that memory address. This signal will pass through the MUX gate as the select signal is MIO.enable, which is 1. It will pass to the MDR, where if the load MDR signal in the control word is a 1, then this data will overwrite the old MDR value. This MDR value is passed into the tri-state buffer with the gate signal gate MDR. When this value is a 1, the value in the MDR will be passed onto the system bus. Note that the value in the MDR is also passed to the data in input on the RAM. When the read-write signal is a 1 on the RAM, this MDR value will be stored as the data associated with the memory address stored in the MAR. Additionally, notice that when the value of MIO.enable is 0, the value passed into the MDR comes off of the system bus. Finally, the RAM will output a ready signal R when it has completed its memory transfer. With that, the basics of the memory unit are covered. The register file is a standard 8x16 file. It stores the general purpose registers R0 through R7 that are used by program instructions to carry out data and memory manipulation amongst other tasks. It's helpful to go through a component and inspect its inputs and outputs to determine its function. Let's break down all of the signals attached to the file. Since we know the size of the register is 8 or 2 to the 3rd by 16, the bus lengths of these signals should be of no surprise. Let's look at these signals a little broadly before discussing them individually. There are 5 inputs. DR, standing for Destination Register. LD, stands for Load. SR1, Source Register 1. SR2, Source Register 2. And finally, an unmarked 16-bit data in. The inputs to DR and SR1 are the outputs of MUX gates that select an input in accordance to control word signals DR MUX and SR1 MUX. Of the inputs to these gates, and also the input to SR2, notice how the signals are portions of the IR signal. The inputs marked 110 and 111 refer to the binary encoding of 6 and 7, alluding to register R6 and R7 respectively. Having specific inputs for R6 and R7 allows the LC3 to use these registers outside of program instruction. The signal marked ld.reg enables the 16-bit incoming data to be written to the memory of the destination register. There are two outputs, SR1 out and SR2 out, which carry the 16-bit values stored in source registers 1 and 2. Now that the function of the register file has been laid out, there are some important specific functions of the registers that are crucial to understand. Register R6 serves an important function as the stack pointer. The stack pointer points to the location of memory address where the instructions on the register allow manipulation of the data stored in these addresses. The role of the stack pointer in its various applications is covered outside this video lecture. Looking at the LC3 instruction set, we can see that various instructions involve manipulations with the program counter and register R7. R7 serves as a sort of bookmark that keeps track of where a program leaves off when it jumps to a subroutine, JSR or JSRR, returns from a subroutine, RET, or executes a trap instruction. Working alongside R6 as the stack pointer, multiple PC values can be stored sequentially and recalled, allowing the function of nested subroutines, or subroutines within another subroutine. Much of the LC3 functionality relies on R6 and R7, so their IR independent inclusion as source signals should come as no surprise. This lecture ends with exploring the role of program registers, or registers that facilitate the program's operation. The three program registers of note are the program counter, or PC, the instruction register, or IR, and the condition codes, or CC, sometimes referred to as the NZP values. The PC register contains the value of the memory address location of the next instruction to be executed. The value of the PC can be changed by three methods as shown by the MUX gate leading to the PC input. When load.pc is a 1, the value of PC will update according to the PC MUX selection. The PC will either be updated with 1, a value passed onto the system bus, 2, an updated PC added to an immediate specified by the instruction, or 0, an incremented PC. The value of the PC will be passed onto the system bus if the gate PC value is 1. When the PC is loaded onto the bus, it is passed into the MAR through the RAM, where the instruction given at the PC location is passed through the MDR back onto the bus, where it will be passed into the IR when load.IR is 1. Notice how the IR branches off into many bit segments. The values in the IR influence much of the data path. While we're here, we can also see the condition code registers that store the values of N, Z, and P. During all operations, the value on the bus will be parsed through logic to determine if the value is negative, 0, or positive, N, Z, or P. When the load.cc signal is 1, these values will be written to the registers. As the name suggests, the condition codes allow the program to work with conditional statements, which is incredibly useful for implementing branches in program code. Notice that many of the instructions in the LC3 set the condition codes. They are marked with a plus at the end of the instruction name in the left column. That completes the overview of memory in the LC3. To recap, we covered the memory unit, consisting of the 2 to the 16 by 16 RAM, the memory address register, and the memory data register. We covered the 8 by 16 register file, including the special roles of register R6 as the stack pointer, and the interaction of register R7 with the program counter, or PC. And finally, the program registers. The program counter, the instruction register, and the condition codes, including how they interact with one another, and how they influence the execution of the program. To further explore this topic, please consult our other videos or our EC290 resources on Piazza. Thanks for watching!